As an example, let's use A equals 0.1 millimeters, which would be a typical width of a slit that you're using for optical experiments, and L equals 1 meter, again, fairly typical. So we want to compare L with this square root. So if you plug in the numbers for L squared plus A over 2 quantity squared, that turns out to be 1 meter plus 1.25 nanometers. So the difference in these two path lengths is 1.25 nanometers. You want to compare that with the wavelength of light, which is about 500 nanometers for visible light. So this is an essentially negligible difference in path length compared to this wavelength, which means that the waves from all of these emitters are going to be in phase when they get to this point that's straight across from the center. And so if we make our graph of intensity, there will be a peak in the intensity at that point. However, if we go off to some point on the side that is significantly off to the side, there will be real path length differences. Let's say between this top point and this point, which is halfway down our slit, there is an important path length difference between those. The analysis of this is just the same as it was for the 2 slit, except now the hypotenuse of the triangle is A over 2. So if we call this angle theta, the path length difference would be A over 2 times sine theta. I want to consider the case of when A over 2 sine theta equals a half a wavelength. So if A over 2 sine theta equals lambda over 2, that means I would get destructive interference between this point and this point. But if I consider the next point down, this point here and this point here, those two also have a path length difference of a half wavelength. And then if I go to the next one down, let's say this point and this point, they would also differ in path length by a half a wavelength. So I'm going to get pairwise cancellation, and so for every point in the top half of the slit, there will be a point in the corresponding position in the bottom half of the slit that cancels the wave from it. So I'm going to get a dark spot at this position. So this gives me a dark spot, and I could write this as A sine theta equals lambda, or theta is approximately equal to lambda over A. That's where that dark spot occurs. So again, if I plot the intensity, it's going to go through a minimum here and start to come back up a little bit, and it's symmetrical. But there's no other place in this case where we get full constructive interference. The only place where that happens is in the straight ahead direction. So it never comes back up very far. It's just a little bit. So almost all of the energy is in this central maximum. And so that's why we focus on this angle for the first minimum. So this is theta of the first minimum for a single slit diffraction is approximately given by lambda over A. Again, this is for single slit diffraction. I'm going to put a start box around this and watch carefully. 1, 2, 3. This is actually the most important equation in our entire course. And part of the reason that it's so important is that we use it in a lot of different contexts, as you will see over the next week or so of the course.